So this particular problem is about taking one single particle as a reference and then seeing how the other particle travels with respect to that. So 3 points are located at the vertices of an equilateral triangle whose side equals A. They all start moving simultaneously. Velocity v constant in modulus. So by modulus it means magnitude. That is, their velocity magnitude is constant, with the first point heading continuously for the second, second for the third, and the third for the first. So it's like the first is always uh, like moving in the direction of the second particle, second towards the third, third towards the first. So how soon the points converge? So it's actually a this looks difficult, but is actually a simple question. So let's consider 3 points. Initially this is moving in this direction, this is moving in this direction, this is moving in this direction. So they keep moving in like each other's towards each other until they meet at the center of the triangle, because their paths would be roughly like this, something like this, right? Because at every instant they would move closer to each other. So like for the next instant they will move, let's say, over here, then this will go in this direction, this will go in this direction, and this will go in this direction, something over here, over here, over here. So basically it's like just for in like just to show how what will be the path taken by them. However, the magnitude of the velocity is constant. So in such cases where particles are moving towards each other, there obviously the directions are changing at every moment. So it is easier to deal only taking two particles at a time, right? If we take only two particles and we let's say we are sitting on this particular particle A, particle B, we are sitting on particle A. That is, with respect to particle A, how is particle B moving is what we need to see. And obviously, like, their distance initially is A, initial distance equal to A, and final distance, this is with respect to, now everything is with respect to A, capital A, right? Point the particle capital A, capital B are two particles, capital A with respect to capital A, this is the thing. Now now with respect to capital A, so B's velocity is anyway in this direction, right? So and velocity of A is in this direction, but you are sitting on A, then velocity, I'll write it as velocity of B with respect to A, right? So we have to be very clear about one thing. So velocity of B with respect to A in the direction of BA, because, right? And one more thing which is why we can do this is the direction between the velocities is always the same. The angle between the velocities is always the same, because the particles, they always like curve, the basically the direction of the velocities change by the same amount after every time delta t. So their angles, relative angles, always remain the same, although their absolute directions are changing. That is something we need to keep in mind. So velocity of B with respect to A in the direction of BA, right? So in the direction of BA, if we see, I'll again draw in the direction of BA. So this is 60 degrees. This is like a equilateral triangle. So the component of B, this direction is V cos 60 degrees, and velocity of A is anyways V, right? So VBA in the direction of BA is v cos 60 degrees in the direction of B. This is particle A's velocity in the direction of AB. So VBA is essentially V velocity of B in the direction of BA minus velocity of A in the direction of BA. So minus velocity of A in the direction of BA is actually minus V, because the A moves in the direction of AB with a velocity magnitude of V. So it is minus V. This becomes V by 2 plus V, which is 3V by 2. This is VB in the direction of BA. Hence, time taken is equal to BA by VB with respect to A in the direction BA. Now what is BA? BA is basically the side of the equilateral triangle, which is A, and VBA, this is A, and VBA is 3V by 2. It is nothing but 2A by 3V. So yeah, that's that. Thank you.